Thank you. Is my screen visible?
Yes.
It is, yes.
Okay, thank you. So I had posted some the answers to some of the questions that came up yesterday and day before. But this is in Slack, but I might have missed some questions. So in case I have missed something, please send me a message. I'll either post it on Slack or we can discuss it tomorrow. Okay, but whatever questions I remembered, I tried to answer in Slack. So let me remind you what we did yesterday. So basically what we did was to count the number of BPA states of a given charge in type 2B on K3 times S1 times S1 tilde, and then compared log of minus B6 with entropy S world. So here again, this is what I posted in Slack. I had said yesterday that B6 is positive. In fact, for the black holes, B6 is negative. So what the answers that I gave yesterday were for log of minus B6. So today I'll just discuss some of the generalizations of this. Okay, but not, I'll just state the results without giving any details. So first of all, this has been generalized, the exact same kind of counting. To a wide class of n equal to 4 theories. So this includes orbifolds of type 2B on K3 times S1 times S1 tilde. Okay, so let me write this as quotiented by Zn, okay, where this acts by 2 pi over n shift on S1 and some supersymmetry preserving transformation in K3. Okay, and there are several such transformations that are known in K3. So that's what we do. And you have a similar description also in the heterotic side. Okay, so this is one class. Okay. The other class for which this has been studied is 2B on, you replace K3 by T4. So I could have written it as T6, but let me write it as T4 times S1 tilde. Again, you mod out by Zn. Okay. And now Zn again acts by 2 pi over n shift on S1 and half supersymmetry preserving transformation on T4. Okay. It's half supersymmetry preserving because if we just start with 2B on T4 times S1 tilde, that actually has n equal to 8 supersymmetry. Okay, that corresponds to 32 supercharges. So you want to break half of it, and that breaking is done by this orbifolding, okay, where you just act by 2 pi by n shift on S1 and half supersymmetry preserving transformation on T4. So while this covers a wide class of n equal to 4 theories, this doesn't cover everything. Okay, so there are some n equal to 4 theories that are known for which the counting has not been done. Okay. And those typically are the ones where you mod out by a product of two Zn groups. Okay. One which acts by 2 pi by n shift on S1, the other one acts by 2 pi by n shift on S1 tilde. Okay, so those class of models, okay, one believes that there should be a similar counting for those class of models, but that counting has not been done. So what one finds in this class of models, that in each case, the partition function, okay, you can again define a partition function as a function of rho, sigma, and v. This is given by of some subgroup of sp2z. Okay, you don't have the full genus 2 modular group, but some subgroup. Okay. Also, in these class of models, the S duality group is broken to a subgroup of SL2Z. But the structure remains the same. Okay, structure of wall crossing remains the same. Okay. And one finds that if you take again log of minus B6, that matches the world entropy up to ordered charge to the 0. On the left hand side, because you have the exact results, we can expand it to any order that we like. But the computation on the right hand side is difficult, and it's difficult to go beyond this order. Okay, that's why the comparison has not gone beyond that. So this is one class of theories. Let me now mention some other class for which the exact counting is known.
Sorry, is there a heterotic description of these models as well? Because the black hole is easier to see in the heterotic description.
Yeah, there is a heterotic description for these models as well. Okay. For these particularly, because type 2b on K3 times S1 tilde, you can dualize into heterotic. And then you just dualate by dualate. So first you can take T duality on S1 tilde, which makes it type 2a. And then you take the orbifold of the corresponding heterotic side. So there is indeed a description on the heterotic side also for these models.
Okay, thanks.
So here, of course, there is a heterotic description, but there is a heterotic like dual description, okay, which is another version of type 2. And you can use that description where the charges look similar to what you saw in heterotic.
Okay, thanks.
Okay, so what I was saying is the exact counting also exists for the following theories. You have the counting for type 2b on T6. This, in fact, is the simplest theory in some sense. Type 2b on T5. Also type 2b on K3 times S1. This, in fact, is the one that contains Strominger-Hoffa. Or more generally, what is known as a BMPP black hole. That's a rotating version of Strominger-Hoffa. So again, one can compare the log of mode index to the entropy. Okay. So here what the result is that you get the leading contribution to this agrees with the Bekenstein-Hawking entropy. But then there are corrections of order log of charge, okay, which was not present in the n equal to 4 stories. Here there are correction of order log of charge. And these do not come from world entropy. Okay, so this requires going beyond world entropy. And today I'll briefly outline how exactly this computation is done from the macroscopic side. Again, from the microscopic side, of course, you just take the index and expand it. Okay, then you have to basically develop the tools for doing this asymptotic expansion, but that can be done. So from the microscopic side, there is no issue of expanding it to any order that you like. But from the microscopic side, but on the macroscopic side, okay, going beyond the leading order requires some effort.
Has any counting of this form been done with less than 16 supercharges?
Less than, no. There is no counting with for less than 16 supercharges, exactly.
I see.
At least not that I know of. Half BPS, okay. I mean, there are of course countings of fundamental string states, but those don't really give finite area black holes, right? So they are not good for comparison with black holes. States carrying charges which would become black holes, right? Those have not been counted. Okay, so the rest of the lecture today will be on macroscopic analysis.
Excuse me, can I ask a question?
Yes, go ahead, please.
In the previous page, you said that for those theories, you need to go beyond the world entropy expression. So what exactly do you mean with that? Like, is there a proposal of an entropy that can give those corrections? There are logarithmic.
Yeah. So that's what we are going to discuss today.
Thanks.
We'll see what is required to get these logarithmic corrections. So we'll try to generalize the notion of world entropy. Okay, we'll see where the world entropy comes, and then we'll go beyond and see how to get those log corrections. Is that okay?
Yes, perfect. Thank you.
So we'll see that they basically come from quantum correction, but you have to, I mean, just wait for a few more slides, and then hopefully it will become clearer. Okay. So macroscopic analysis basically means that you are trying to do the analysis from the gravity side to develop the procedure for doing a systematic computation of entropy from the gravity side. Okay. So the first important fact here, okay, which I'll discuss briefly now, is the appearance of ADS2. So for this, let's first consider Reisner-Nordstrom black hole. Okay, so the metric has the following form. Here psi is the usual polar angle. Let me say this. I am using, which is normally called theta. Okay, this is the usual polar angle, which is normally called theta. But I'm using this symbol psi because you are going to use theta for something else. That's the Euclidean time coordinate. Okay, but otherwise, the psi is the usual polar angle. Rho plus minus are the outer and inner horizons. And the extremal limit is when the two horizons coincide. Okay, that's the limit rho plus going to rho minus. So you're going to take that limit, but what you are going to do is that we are going to take that limit not in this rho t coordinate system, but you will introduce a coordinate system that is appropriate to being near the horizon. So what you want to do is that you want to be near the horizon and then take the limit. So let me just introduce this new coordinate system. So first we define lambda as rho plus minus rho minus by 2. Then you introduce a new time coordinate which is scaled as lambda tau. Sorry, I should have called this tau. Okay, so this time coordinate I called tau. Okay, this t is the new time coordinate, lambda tau over rho plus square. And r is 2 rho minus rho plus minus rho minus over 2 lambda. And now we take lambda goes to 0, keeping t and r fixed. So if you take lambda goes to 0, keeping r fixed, right? That means rho plus is going to rho minus, but at the same time, rho is going close to rho plus, which means we are remaining close to the horizon. Okay, that's why this coordinate r is important. Okay, r is in this coordinate system, finite r means that you are always staying close to the horizon. Why we scale t this way, it will become clear because the metric will have the lambda dependence drops out of the metric if we scale t in this way. So what I'm going to do is to now write down the same metric after taking this limit. It's a straightforward exercise, so I'll just give the answer. And what we find is the following. Okay, nice looking metric, but in fact it has nicer properties than what it looks. This metric in fact is nothing but the metric of ADS2, and this of course you can recognize as a metric of S2. So the near horizon geometry of this extremal black hole has acquired an ADS2 factor. Okay. S2 of course was there to begin with, okay, but it has acquired an ADS2 factor. Okay. And as a result, it has more isometry than what you started with. Okay. This has SL2R times SU2 isometry. In fact, what one can show is that this is not a peculiar feature of Reissner-Nordstrom black hole. Okay. The appearance of ADS2 is a generic feature of the near horizon geometry of extremal black holes. Okay, so this is a fact that you are going to use. But this has a very nice consequence, because what it tells us is that this gives a way to calculate the near horizon geometry and entropy without solving any differential equation. Okay, and I'll explain how that works. So typically, when you want to construct a black hole solution, you have to solve a differential equation with some asymptotic boundary condition. and that can become complicated if the theory is complicated enough. But because of this existence of ADS2 times S2 near horizon geometry, okay, we will now argue that it is possible to find the entropy of such a black hole without solving any differential equation. Not only the entropy, but also the near horizon geometry. Okay, at least to a large extent. Okay, we'll see to what extent.
Can I ask a question?
Yes,
Does
go
this-
ahead, please.
Does this also happen if you have scalar fields, like massless scalar fields that couple to,
Yeah.
you know?
Yeah, in fact, I mean, we are dealing with supergravity, where there are lots of massless scalar fields coupled to gravity, right?
Yeah.
But the appearance of ADS2 factor always happens.
Always happens.
Yeah, so it's as you go to the extremal limit, I think there is a general proof also from the gravity side that all extremal black holes have ADS2 in the near horizon geometry.
Okay.
And as far as I remember, this doesn't even require using any particular form of the Lagrangian. All that it uses is that it's a covariant Lagrangian. It's a general coordinate invariance.
I see.
So it's a universal feature of extremal limits.
And this happens for asymptotically flat and asymptotically ADS and asymptotically.
Well, I think the proof that I recall was probably for asymptotically flat cases, but I'm not completely sure. Okay, I can look up the reference and tell you, but certainly for asymptotically flat black holes, this happens.
Okay,
So there is
thanks. Mhm.
Okay, so let me now describe how we make use of this ADS2.
Hello?
So the first step, sorry, was there a question?
Yes. I'm asking how can asymptotic nature can be changed by an near horizon nature can be changed by an asymptotic behavior, for example.
Yeah,
I mean, followed.
My intuition will be no. Okay, but
I see.
as I said, since I don't remember the details of the assumptions, I cannot tell you for sure.
I see.
But yeah, intuitively, I agree with you that somehow the near horizon
So I'm
geometry.
asking, is there any way that globally it can change, or like the intuition says that locally it should not change, right?
Yeah, I mean, as far as I remember, the analysis was local, but again, I'm not 100% sure.
Yeah. Sure.
So that's why I'm not committing myself right now. But I'll try to look up the paper. In fact, I'll post the reference on Slack also.
We have to assume that the horizon of the black hole is much smaller than the cosmological horizon if we are working with all three.
With
I mean, if the cosmological horizon of T Sitter is very close to the black hole horizon, we shouldn't expect the near horizon geometry to be the same.
yeah, so this is, as I said, I mean, what I remember is for asymptotically flat black holes. Let me give you the reference to the paper, right? Then you can check what are the assumptions that have gone in. So for asymptotical flat black holes, of course, there's a question of cosmological horizon, right?
Yeah.
There's embedded in Minkowski space. Yeah, so right now, let's just focus on asymptotically flat black holes. Okay, so what we do is to begin by writing down the most general near horizon field configuration solution consistent with SL2R times SE2 isometry. And it turns out that this isometry is powerful enough to fix the near horizon geometry just in terms of some constants. So for example, for the scalar, okay, one can show that the only possible near horizon configuration is constant. Okay, it doesn't depend on either the coordinate of S2 or nor the coordinate of ADS2. For the gauge fields, the RT component of the gauge field or of the field strength is constant, right? And the psi phi component of the field strength is pi sin psi. Okay, there may be some normalization factors of 4 pi or 2 pi. That depends on how normalized pi, but let's not worry about this right now. And the metric, okay, so you are basically assuming that this is the massless fields in the theory are scalars, vector fields, and metric, massless bosonic fields. So we're just writing down the most general field configuration that you can have. So the metric is parameterized by two independent parameters. Yes.
Professor, can I ask you a question?
Yes, go ahead, please.
Is there a reason you call this SU2 instead of SO3?
No. Yeah, I mean, I'm just thinking of the algebra, so it doesn't.
Okay.
You could call it SO3. But there are, of course, fermions.
Okay.
So SU2 is more appropriate, but at this stage, I mean, we are just using the bosonic part of the symmetry, so it doesn't matter.
Yeah, thank you.
So this form is just what we arrived at for the Reisner-Nordstrom, except that the isometry itself doesn't fix this relative values of V1 and V2. So this is the general form. So now suppose we are given an action which has this structure. L is constructed out of the Riemann tensor, the phi and its derivatives, the field strengths, and so on. It can have arbitrary higher derivative terms. You make no assumption about that. But just from the fact that we have this SL2R times SO2 isometry, one can show that L, in fact, is a constant on the horizon. So this constant, let's call it some function of the near horizon parameters, which are C. So when I write a vector sign, that means basically collection of all the CIs. E, P, and V1 and V2. Okay, it's a function of all this. And the square root of minus determinant G, you can easily see from here, okay, is V1, V2, sin psi. So if you now put it back here, okay, you get the action. Okay, most of the things factored out. So the psi and phi integral just gives you the usual 4 pi as usual. So you get 4 pi V1, V2, F. Okay, actually, let me call this F tilde. Okay, I'm going to use F for something else. F tilde times dr dt. Okay, this is just factors out because nothing depends on r and t. Okay, the integral. And this quantity, let me call F, which is a function of all these variables. C.
Is the Lagrangian constant just because it's supposed to be a scalar? And
Exactly.
as you said before, the scalar is
Exactly.
okay.
Yeah. But you can explicitly evaluate what this is by knowing the form of the Lagrangian. If somebody gives you some arbitrary higher derivative action, you can just substitute this with near horizon geometry and evaluate what this is.
Okay.
Okay, and you can explicitly verify that it's a constant.
Here we're talking about the on-shell Lagrangian, right?
Pardon?
We're talking about the on-shell action, which is the pattern, right?
No, this is not on shell. See, so I'm not claiming yet that these satisfy the equations of motion. This is the most general field configuration consistent with isometries. Right? So it's still off shell. We take the form of the Lagrangian and substitute this form of the field configurations. We have not used equations of motion anywhere so far. Is that clear?
Yes, thank you.
Yeah, so this is not on shell yet. Okay, we are now going to impose the equations of motion. So let me write again. So you have S, which is a function of all these variables, C, E, P, V1, V2. integral dr dt. Now we use the fact that equations of motion means that S must be extremized. So it must be extremized with respect to the fields. Okay? But if you have an isometry, okay, you can just restrict to extremization within the isometry class. Okay? Which means that you can just extremize with respect to the parameters that you have introduced, that is C, V1 and V2. Okay? These are of course gauge fields. You don't extremize with respect to E and P. I'll say explicitly what you do here. In fact, the fact that E and P are taken to be constant, okay, that automatically says that the gauge field, the equations are satisfied. Okay, you don't have to impose the gauge field equations anymore. Okay. So we have these equations. So extremizing this means that you have to say extremize with respect to Ci, del F del V1 equal to 0, del F del V2 equal to 0. P is an input parameter. P is like the magnetic charge. Okay, that's the magnetic charge of the black hole that you are going to study. Now, naively, you might expect that E should be the electric charge, and indeed, in the Maxwell's theory, right, the electric field is a measure of the electric charge. Okay. But in general, if we have a complicated hard derivative theory, okay, then the correct definition of electric charge is not E, but it involves the derivative of the action with respect to the field strength, okay, which in this normalization is basically del F del EI. Okay, so this is the electric charge. So the idea is that you think of P and Q as something given, okay, the magnetic charge and electric charge, and you determine the near horizon geometry. This C is V1, V2, and E by solving these equations. These three equations and this. So let me put them in a box. Okay, of these, the first three are following from equations of motion. This is just a definition of the electric charge. Now, this can be written in a slightly more symmetric way by introducing a function. So we define E as 2 pi sum over I EI QI minus F. In that case, these equations can be written all as extremization of E. Okay, this 2 pi I'll explain later. 2 pi is just right now just a convenient normalization. Okay, but it will be useful later. So then all these equations can be rewritten as del E del Ci equal to 0. Okay, because this equation now just becomes the del EI of E is equal to 0.
Hi, sorry, could you repeat the argument as to why you can vary the action after plugging in that form for the fields? Because usually you can't do that unless you have some sort of constraint, unless you have some consistent truncation.
Yeah, so here the point is because we have a symmetry, we are looking for the most, we are done the most general field configuration consistent with a certain symmetry. It is a consistent truncation.
Okay, so the statement is that imposing this symmetry is a consistent truncation.
Exactly. In fact, imposing any symmetry is a consistent truncation, typically. Right? Because it's an isometry. So if you vary with respect to the field that respect the isometry, okay, then those give the equations of motion. If you vary with respect to a field that doesn't respect the isometry, then the variation we expect automatically to be 0 because the field configuration has been restricted to isometric field configuration.
But can't you have some mixing terms if the symmetry, if it's just a generic symmetry you're imposing?
But if it's an isometry, then you cannot have a mixing, right? See, this is the symmetry of the theory. Okay, it's an isometry of the vacuum, but it's also a symmetry of the
Mm.
Lagrangian, right? Because it's coming from part of a diffeomorphism.
Okay.
Yeah.
Okay.
So there's a mixing term between invariant and non-invariant terms, non-invariant field configurations. Okay, so once you have determined the near horizon geometry, so you can see now that these are actually just algebraic equations, right? You have to compute E and then take these derivatives. This gives you some polynomials in C typically, and that's what you have to solve. And once you have solved the near horizon geometry, we can also calculate the world entropy. So remember that I wrote down the formula for S world yesterday. Okay, it involves the derivative of the Lagrangian with respect to the Riemann tensor. But after you plug that in and do some manipulations, you find a surprising result that this is actually E at the solution. Okay, this requires some work to show. Okay, later on we'll see a simple way to understand this. Okay, but if you just directly try to use world's formula, you need to do some work, but eventually you arrive at the result that E S world is just E. Okay. So this in fact gives you a way to calculate not only the near horizon geometry but also the entropy, okay, without ever solving any differential equation. But it also explains something else, okay? Namely it explains attractor mechanism. Okay, it explains attractor mechanism but also extends it. Okay, the original attractor mechanism that you saw was for the two derivative action where you use the Bekenstein formula. Okay. But now this explains attractor mechanism for the general S world, for S world. Okay, that means including all the higher derivative corrections. Okay. So what is attractor mechanism? The fact that S world depends on Q and P and not on asymptotic moduli, not on asymptotic values of moduli. Okay, so remember the differential equations. Let me write them down here. So we have del
Can I ask a
E.
question?
Yes, go ahead, please.
Does the attractor mechanism depend on supersymmetry, or is it independent of that?
No, it doesn't.
Okay.
It only depends on the fact that it's an extremal black hole, and that's what I mean. The proof will make it clear that it doesn't depend on supersymmetry at all. Even though originally it was derived for supersymmetry, okay, and for two derivative action. But this, the argument that I'm going to give is going to make it clear that it doesn't really depend on supersymmetry.
Okay.
With some small caveat that I'll also mention.
Okay, thank you.
Okay, so these are the equations.
Sorry, can I ask a question?
Yes, go ahead, please.
I might have missed something, but seems to me that here you wrote down answers for the solution of the fields, which is valid only close to the horizon of the black hole, and then you computed that swap, right?
Yes.
So, okay, so in this case, the idea that you can trust this to be the entropy of the whole space-time, even if you're looking only at the near horizon region, is because you expect the entropy of the black hole to be dependent only on the surface gravity or any way, in some sense, to some property that you can see just from near the horizon of the black hole.
Exactly, because S world is given by a formula that is integrated over the horizon of the black hole. Right? Remember the formula for S world that I gave, that involves an integration that runs along the horizon. Okay, so that makes it clear that the world entropy depends only on the near horizon geometry.
Okay.
Then we expect it, right? Then why is it surprising that S wall doesn't depend on the asymptotic values of moduli?
Because near horizon geometry could depend on the asymptotic values of the model line. Right?
I see.
You fix Q and P, also the asymptotic model line. So the solution certainly start from the asymptotics.
So asymptotic moduli, you mean by asymptotic moduli, you don't mean CI and EI, right?
No, CIs are the values on the horizon.
Right. Yes. So what is asymptotic moduli here in this context?
Here you don't fix asymptotic model line. Right? I mean, this, whatever I have done so far doesn't depend on the asymptotic model line, but we will see that the near horizon geometry could still depend on the asymptotic model line, right? And we will see how it could happen.
I see.
Nevertheless,
Okay.
we will see that the S world doesn't depend on it.
I see. Okay. And why is it called attractor mechanism?
Because of this fact that somehow the black hole entropy gets attracted to some particular value that is independent of the asymptotic model line.
I see. Okay. Okay. Thanks.
Okay. So the first possibility is that these equations fix Ci's Vi EI completely. Okay. If that happens, then of course there's nothing to prove, okay, because then that shows that the near horizon geometries are only dependent on Q and P and nothing else, right? So that cannot depend on the asymptotic model. Okay, so that's clear. Okay, so this means that S world or E at the extremum, at the solution, depends only on QP. But the second possibility is that these do not fix that, let me say carefully, that E has some flat directions and therefore the parameters don't get fixed completely. The near horizon parameters. In that case, they could depend on the asymptotic model line. Okay, it could where they land up, okay, near the horizon could depend on where you started at infinity. So the near horizon geometry then in that case can depend on the asymptotic model line. But you see that this still means that E by definition is independent of the flat directions, right? Otherwise you would have fixed those model lines. So E is still a function of only Q and P. So this is what proves that even if the near horizon geometry, okay, is not completely fixed and it depends on the asymptotic model line, the world entropy that you calculate actually doesn't depend on the asymptotic model line. Now for this, it's important that the function that you extremize is the same function that gives you the world entropy. Okay, if world entropy was not E but something else, then this argument wouldn't work. But the fact that you actually extremize it to determine the near horizon geometry and that the same function gives the world entropy is behind this attractor mechanism. Okay, that E is only a function of Q and P and not on the asymptotic model line.
I'm a little bit confused about something. So
yes, go ahead.
In the supersymmetric case, it makes sense that the black hole entropy, say the BPS case, the black hole entropy wouldn't be a function of the asymptotic moduli because, you know, as you move around, the number of BPS states is protected or something. But if you had non-supersymmetric, so non-BPS, but still extremal black holes, is not clear to me why we would expect this to happen.
Yeah, true. From the microscopic side, you don't know. Yeah, I mean, there is no reason why that should happen.
Right.
But if you just think in terms of extremal black hole, I mean, it's a property of gravity that seems to happen. Yeah, but I agree with you that there is no, I mean, reason why you should expect this from the microscopic counting.
Is there any microscopic explanation for this, or this is really a surprising
Not
fact
that I know of. No, I don't think there is any microscope, because we don't really understand that these non-BPS extremal black holes very well from the microscopic side.
Mm-hmm, mm-hmm. Great, thanks.
Thank you. Okay, there is one exception to this, and let me mention. And that is that if there are multiple disjoint solutions, namely, they are not part of a family along which E remains constant, but there could be just multiple disjoint solutions of the equations of motion, to the equations. In that case, E may take different values at those different solutions. Okay, there's no argument can take different values at those different solutions. In that case, what could happen is that for some range of asymptotic values of the model I, the solution may get attracted to one particular solution, near horizon solution. And then as you go to another domain, okay, the solution may actually reach the near horizon geometry that you get maybe the other solution. And in that case, the entropy can change, okay, and it can jump across the, as you cross from one domain to another. But there are no known examples, at least for supersymmetric black holes, of this. For non-supersymmetric black holes, I have a feeling that by choosing appropriate Lagrangian, you may design such things. Okay, whether that can happen in string theory, I don't know. Okay, but at least in supersymmetric black holes, you don't know of an example where that happens.
I have kind of a random question. Can this whole story also go through for Kerr black holes?
For Kerr black holes, yeah, it is. Well, it's not as good for Kerr black holes, because what happens there is that you don't have the SU2 isometry. So when you write down the generic solution, you have to allow for arbitrary dependence on the theta coordinate. Okay, you only have the phi transition symmetry. So you cannot get the solution, the extremal kind of solution, just by solving a set of algebraic equations. But you have to basically solve an ordinary differential equation in theta.
Okay.
So that's the story for Kerr black holes. It's still much simpler than solving the full set of differential equations.
Okay, but there's still some notion that like the moduli get fixed on the horizon, but just maybe not in like a spherically symmetric way.
Exactly, that's
Okay.
it. It can be arbitrary functions of theta.
Can I ask something?
Yes.
You said that if these are multiple disjoint solutions, do I think of that as there being a moduli space of solutions, and the moduli space is disconnected and E is a constant on every connected component?
Yeah, you could. That's a more general case. Yes, that you can say.
Okay, but
Yeah.
E is a constant on every connected component.
Yeah. E will be a constant on every connected component. Exactly. So that's a flat direction.
Yeah, thank you.
Okay, now let me say something about quantum corrections. I don't know how much I'll be able to say, but let me say this anyway. Now, naively, you might expect that one could simply work with one PI action. And apply the same formalism. Okay, that basically means that what you are calling L is replaced by L1 PI. And this works to a large extent, okay, works except for terms that are non-local. Because if you recall that the one ingredient of this analysis was that we have to write S as square root of minus determinant G times L. As long as the one PI action is local, you can still apply this. But if it has non-local terms, then of course it cannot be written as a single integral. Okay, and then you have to do something more. Okay. And these typically do arise whenever there are massless fields. And in gravity, of course, there is always a massless field. That's the graviton. Okay, so you have to do something more to do this. So typically what happens is the ADS to size provides an effective IR cutoff but does not give a local action. Right? Because you really need the ADS to size to provide the cutoff. That means ADS to size, by ADS to size, I meant that parameters V, what we call V1. So it turns out that it is possible to do this quantum correction directly in ADS2, okay, by using a version of Euclidean ADS2 path integral. Okay, so let me try to describe that. So Euclidean ADS2. Okay, we take t to minus I theta. So the metric takes the following form. It's V. Okay, I have dropped the V. I'll not talk about the S2 anymore. Okay, that's there. Okay, but the ADS2 is going to play the major role. So it becomes R square minus 1 d theta square plus dr square or R square minus 1. This looks singular at R equal to 1. Okay, but this is actually non-singular if theta is periodically identified with a period 2 pi. Okay, this is like the standard black hole horizon. Okay, that in the Euclidean time, if you choose an appropriate periodicity, it's non-singular. In fact, this after the appropriate coordinate transformation, you can show that this has the topology of a disk. Okay, perfectly smooth point. R equal to 1 is a perfectly smooth interior point in the geometry. So now, given this Euclidean ADS2, we'll now define macroscopic partition function. This is not to be confused with what we did yesterday. With the Z rho sigma V, that was more like a generating function. Okay, this is the partition function for the macroscopic side. This, in fact, is a function of charges, okay, Z QP. So this is defined as integral over d phi. Okay, this includes integration over all the fields in the theory. Okay, if it's string theory, then all the fields in string theory. E to the minus s. Okay, this much is clear, but we will add a boundary term at ADS2, and I'll explain the reason for this in a few minutes. the boundary term will be this qk integral over the boundary of ADS2 this B of AK. Okay, so AK is the one form gauge field. For every gauge field that you have on ADS2, you multiply by its corresponding charge and you add this boundary term. And this path integral is done over use normalizable modes. In ADS2. You don't see the S2, that's why the PKs are hidden. But of course, they are very much there. They put the boundary condition on asymptotic boundary condition on the psi-phi components of the fields. Now, why is there a boundary term that is needed? Okay, normally in Maxwell electrodynamics, you don't add this boundary term. Okay. So this boundary term, I mean, you are probably familiar with this Gibbons-Hawking term in gravity. Boundary term is the analog of the Gibbons-Hawking term in gravity. And basically it's needed because in ADS2, not in arbitrary ADS, not in higher dimension ADS, in ADS2, we integrate keeping charge fixed and letting chemical potential fluctuate. Okay. So chemical potential is the constant mode of AK. Okay. And the charge mode is the electric field. Normally in higher dimensional ADS, what happens is the charge mode actually falls off rapidly compared to the chemical potential, right? Chemical potential is a constant field at infinity, okay? Whereas the charge mode typically corresponds to a decaying gauge field. But in ADS2, okay, the charge mode actually grows because charge mode means it's constant electric field, right? So A theta is linear in R. Okay, so that's the growing mode, non-normalizable. So that has to be kept fixed. And the chemical potential, that means the constant mode of AK has to be allowed to fluctuate, okay, because that's normalizable. And that's why you need this extra boundary term. Okay, this one can do a little bit careful analysis and figure out that this is the boundary term you have to add to compensate for this fact. Normally, the way you do the integral over the gauge fields is reversed in the case of ADS2. Okay, so we'll proceed with this. Now let me make two claims. The first claim is that this object Z macro has the form d to the minus c times L. So what is d? D is a constant. C is some other constant. And L is the length of the regulated boundary of ADS2. It's a boundary of ADS2. Okay. So this could be regulated by, say, putting R less than or equal to R lambda, okay, for some cutoff, okay. Or more generally, R less than or equal to lambda times function of theta. Okay, it doesn't matter. the claim is that Z macro always has this form. The second claim is that D gives this constant over here, the full quantum corrected degeneracy. Other questions?
Sorry, like how do you, well, how does one do this? Because like if S is quadratic, then maybe one can just compute the determinant of the fields and get this ADS2 partition function. But more generally, how does one do this and see that this is the form?
Okay, I'll give you the argument as to why this should be the case. And then I'll tell you, you are right that you can, if S is quadratic, then you can do this. Okay, but you can also, I mean, even before that, you can do the semi-classical analysis. Okay, to verify this. Then at least
saddle point analysis.
Analysis will give you the S word, right?
Right.
Okay, so that you can verify. You can verify that. Okay, and then you can calculate the quadratic fluctuations. But in principle, you can do higher order fluctuations. The only issue you have to worry about is UV divergences, right?
Yes.
And in string theory, in principle, all the UV divergences are under control. Now you may say the practical way of, I mean, to practically implement this may be hard, and you have to devise tricks. But this is a general statement that if you could do this, then you will get the full quantum corrected degeneracy.
And log of T is the entropy.
Log of D will be the entropy. Exactly.
Okay. All right. Thanks.
Okay. So in my notes, actually, I have the semi-classical limit, but let me just state the result then without worrying about the proof. So I'll leave it as an exercise. Okay. In the semi-classical limit, well, I should say classical limit because you are just evaluating the, in the classical limit, okay, Z macro is just the exponential of whatever we had at the classical solution. And this, I mean, it's a reasonably easy exercise. Basically, you have to translate from the Euclidean to the Lorentzian variables that we had introduced. You can show that this is given by exponential of minus 1 over 2 pi e integral 1 to lambda dr integral d theta. Why 1 to lambda? Because you remember r is larger than or equal to 1, right? Because at r equal to 1, that's a regular point in the interior. Okay, the geometry stops there. Okay, that's why r has to run from 1 to lambda. So this integral gives you exponential minus 1 over 2 pi e times lambda minus 1 times 2 pi. On the other hand, the length of the boundary, L, is 2 pi. 2 pi comes from theta integral times the, basically the g theta theta, that's square root of lambda square minus 1. Okay, because this is at r equal to lambda. So this is 2 pi lambda plus order 1 over lambda. Okay, which goes to 0 as a lambda goes to infinity. So this I can write as exponential of e minus, let's see, 2 pi cancels. So e minus e lambda, so minus e times L over 2 pi. Okay. So this I am supposed to write as d to the minus cl, right? Okay. So c is here E over 2 pi, but what is important is D, where D is exponential of E. So in the semi-classical limit, okay, in the classical limit, it does give correctly the exponential of the world entropy. But let me now indicate the general argument behind this. Okay, and I'll then describe some consequences. So Z macro, okay, the ADS to part Euclidean ADS to partition function. If you use just the naive ADS CFT correspondence, this should be Z CFT. And the CFT lives on a circle, right? Circle at the boundary. Topologically, it's a circle at the boundary, circle of length L. Now, if we follow further the dictionary of ADS CFT correspondence, okay, what is CFT1? So CFT1 should be the IR limit of the quantum mechanics of the microscopic system we analyzed. Okay. So D pi R, okay, so this microscopic system, remember we had various kinds of oscillators and so on. So this has a gap separating the ground state, those are the BPS states, from the first excited state. So in the extreme IR limit, basically only the ground state remains, right? Everything else is irrelevant. So then Z CFT1, okay, in this extreme IR limit just becomes the ground state degeneracy, that is D exponential minus E times L, okay, where E is the ground state energy. And now you see that if you compare this with this, then the constant piece, the overall multiplicative factor after you have taken out the linear term in L in the exponent, is the degeneracy. Okay, so that's the general proof that this is the way we should extract the degeneracy from the macroscopic partition function. I think I have about 5 minutes, so let me say something more. So one application of this is logarithmic correction. To black hole entropy. These we can show basically arise from one loop determinant of massless fields on ADS 2 times S2. And this can be calculated. The algebra is a little complicated, but because the full set of eigenfunctions for scalars, spinors, vectors, etc. are known on ADS2 and S2. Okay. So basically, we expand all the fields in this full set of eigenfunctions of the Laplacian on ADS2 times ADS2 and S2. Okay. The difficult part is typically the supergravity Lagrangian, because there are background fluxes. Okay, it mixes all of these fields. Okay. And you have to diagonalize it properly to calculate the determinant. Right? So that part is algebraically complicated, but it's something that can be done. The other part that is a little involved is because that there are some zero modes, okay, which are exact zero eigenvalues of this Laplacian. So they do not appear in the action. So you have to do the integral over those in a different way. And the way we deal with the zero modes is to first observe that the zero modes that we get are essentially almost pure gauge, except that the gauge transformation parameters are not normalizable. Okay, that's why they are not pure gauge. Nevertheless, what you can do is that you can change variables from the fields to the gauge transformation parameters. Okay, even though they're not normalizable, this is just a change of variable. The Jacobian, okay, has to be treated carefully. That gives dependence on the ADS radius. And then the integration over the gauge volume just factors out, giving a constant that doesn't depend on any of the charges of the theory. So that's the way you do this computation. And the upshot at the end is that you can extract carefully terms that are logarithmic in charges. So what I'm going to do is to just show you some general results. Here, I think I have the PDF file here. Okay, so this is in fact I have included in the notes that I have uploaded. Okay. So this basically is a list of various theories where you have the microscopic calculation, or where you have the macroscopic calculation and the corresponding microscopic comparison. So this theory is what you saw before. N equal to 4 supersymmetric theories in D equal to 4, the whole variety. Okay. There you didn't encounter any logarithmic contribution, okay, microscopically. Okay. And indeed, when you do the macroscopic side of the calculation, you find that there are no logarithmic corrections. Okay. Not because of any trivial reason. Okay. There are logarithmic corrections from scalars, vectors, tensors, and so on, but at the end, they all add up to 0. So there is perfect agreement between the absence of logarithmic corrections as predicted from the macroscopic side and the microscopic side. This is the simplest theory in some sense. Type 2 on T6 has maximal supersymmetry. Here, the microscopic theory shows there is a logarithmic correction, and that agrees with the macroscopic side. So these are the macroscopic results. Here you see the BMPV black hole. And this is a BMPV black hole with J equal to 0. That's the Strominger-Hoffer black hole. Again, from the macroscopic side, you can calculate the logarithmic corrections. From the microscopic side, since the exact counting is known, you can expand and see what corrections you get. And again, there is perfect match between the two theories. In the rest of the table, okay, you will see results that you get from the macroscopic side, because from the macroscopic side, all you need is a supergravity. Right? Once you have the field content and the supergravity Lagrangian, you can just diagonalize and calculate the logarithmic corrections. Okay, because this is just one loop determinant of massless fields. So there are results known for n equal to 2 supersymmetric theories, n equal to 6, 5, and n equal to 3 supersymmetric theories. But there are no microscopic counting available for these. So you can see that higher supersymmetry doesn't always make things easy, because n equal to 6 certainly has more supersymmetry than n equal to 4. Nevertheless, nothing is known about the microscopic counting in these theories. But on the macroscopic side, you have these nice results, which would be nice to verify if one could ever do some microscopic counting.
Is there any realization of those theories like n equals 6 and n equals 5 in string theory?
Yeah, n equal to 6 there are certainly. N equal to 5 and n equal to 3, I'm not aware. But they are supergravity theories. But probably with some sufficient effort, one can also construct these. It may already be there. It's just that I'm not aware of explicit construction of these theories as string theory. Remember, n equal to 3, there may be, because n equal to 3, even rigid Yang-Mills, I think people have constructed. So it may be just my lack of knowledge, okay, that I cannot tell you for sure that these theories have been constructed in string theory, but these certainly have been. The reason that the counting is difficult here is because this involves some asymmetric orbifolds, and that makes the D-blend spectrum a little more complicated in these theories. Okay, I think I'm almost out of time, right? So let me just mention 2 things and then I'll stop. Okay, that just maybe 1 more minute. There is some other applications. One is twisted index. Okay. So let's take in n equal to 4 theories. So what we do here is that we calculate. Okay, there are analogs of this is in other theory, n equal to 8 theories also. So you calculate the usual B6 index with a twist. Where G is some Zn transformation that commutes with supersymmetry. So this ADS to CFT kind of analysis that I showed you, you can apply this to this twisted index. And this tells us that the entropy should go, the leading contribution to this should go up as exponential of world entropy divided by n. Okay, if you may mod out by Zn. Okay. On the other hand, you can do a microscopic counting here. Exact microscopic formula is available for this. And again, that gives exactly exponential of S world by n plus corrections. Then we have the sign of the index. I'll not say very much about this. Sign of the index. So ADS to CFT1, this again same idea, can be used to show, to argue that sign of B6 is negative. Okay, and in general, sign of B2n, okay, B2n may be needed for, depending on what kind of supersymmetry you have in the theory, is -1 to the n, okay, in general. Again, this has been tested in many examples, tested in many microscopic examples. And finally, I should mention that there are some attempts for exact evaluation of Z macro. Remember, it involved the path integral over fields. And so these attempts for exact evaluation of this path integral is using supersymmetric localization. Okay, because in supersymmetric localization, that's exactly what we do. Okay, we start from a path integral and then you try to reduce it, somehow use supersymmetry to show that it can be reduced to a finite dimensional integral. Okay, so this is the work of Gabulkar, Gomez, and Murthy. They have a series of papers. And I would summarize them, the results, by saying that they are encouraging. But many things still need to be understood. But they did show that with making certain assumptions, they can reproduce the full charge, 1 over charge expansion using the supersymmetric localization ideas. So I think I'll stop here. Thank you.
Thank you very much, Ashok. So I guess we have time for a few quick questions. So you're aware, there will be an opportunity to ask more questions tomorrow, same time slot. So yeah. Any questions?
Can I ask a quick one? So the CFT1 that you say is, as you said, it's supposed to be the IR limit of the free field theory that you were studying yesterday in this D1, D5 system, right?
Yes.
So how explicit is it? Like, do we know what are the operators of CFT1? Or
Yeah, see, the point is, okay, if you take the deep IR limit, okay, as we discussed, everything goes away except the ground states, right?
Mhm.
So it's a finite
Yeah.
dimensional Hilbert space
Mhm.
with all degenerate states.
And we know
So the
what the
operator-
states are. The
Pardon?
states are just the Fock space of those oscillators, or
Exactly, what we counted, the BPS
I
states,
see.
right? Because all the non-BPS states, because they are separated by gap, they become, in this IR limit, infinitely massive.
I see.
So the CFT1 is somewhat trivial, right? It's just a finite dimensional Hilbert space with all degenerate states.
I see. Yes. Okay. Thanks.
So if n is the degeneracy, then the operators are just n by n matrices.
Yes. Yes. Right.
I had two questions. So the first one relates to the attractor mechanism that you were describing. So
Okay.
you mentioned that the attractor, this is called attractor mechanism because this E function depends only on Q and P.
Yes.
And not on the moduli fields, the asymptotic value of the moduli fields. Now, you showed that to be consistent with ADS2 cross SU2, you need the moduli fields to be constant. And is that the asymptotic constant value of the moduli field that you were describing?
No. So the point is that the moduli fields, what constants they are, that is determined by these equations. Go back. One more step. Step maybe. Yeah. Okay. Actually, these equations are there. So what constants they are determined by solving these equations. That's the near horizon values of these constants. Asymptotically, the fields take different values. So what happens is that as the solution evolves from asymptotic region to the near horizon region, the scalar fields change. They are functions of the radial variable. And when you reach the horizon, they take the values that are given by solutions to this equation. So these constants are in general not the same as the asymptotic values of those scalar fields. Right? So in a sense, those values get attracted to the solutions of this equation.
Okay.
Right? And that solution may not be unique, so there may not be a unique attractor, there may be a family of attractors. Okay? But the world entropy on that family takes the same value. So the world entropy is genuinely independent of Q and P, whereas the actual asymptotic, actual near horizon values of the scalars may have some dependence on the asymptotic moduli if these equations don't fix them uniquely.
Okay. So, I mean, can I there are in very simplified, for example, if you take Einstein-Dilaton action, and if you write down the solution for that, you can construct extremal black holes with asymptotic scalars, with the value of the scalars equal to the asymptotic value of the scalars in the metric. Now, can I say that if I then do this coordinate transformation to write it as ADS2 cross SU2, then the asymptotic value of the scalars will become the value of the scalars at the horizon? Can I rewrite the metric in that form?
Okay, you are saying that there are solutions to the Einstein-Dilaton equation, where the scalars, you fix the asymptotic values of scalars to whatever you like, and there are still solutions, right?
Yeah.
Those solutions typically will have the scalars changing as a function of radial variable.
Right.
So what I'm saying is that if we fix the charges, then the scalars must change as a function of the radial variables in such a way that by the time you have reached the horizon, they solve these equations.
Okay.
So these equations don't by themselves tell you how exactly the scalar fields vary radially, but they tell you the endpoints. Okay? The endpoint at the horizon is given by solutions of this equation. Asymptotic values are something that you set. you decide that you start with the scalar fields with certain values.
Okay.
And then the solution automatically does this process of evolving the scalar fields from the asymptotic, whatever they are, you have set them asymptotically to whatever they are supposed to be on the black hole horizon.
Okay. The second question I had is related to the chart that you showed towards the end. So you mentioned that in n equals 2, d equals 4, we don't have a microscopic counting. Now, if I'm not wrong, I think in supergravity side, you have this nice reduction of d equals 10 supergravity on T6, and then you get the n equals 8 supergravity, and then you do consistent truncation, and you're getting n equals 4 and n equals 2 from the n equals 8.
Yes.
So I mean, it's quite nice on the supergravity side. And you also showed that the n equals 4 can be constructed, the T6 reduction. The heterotic string reduced on T6 can be constructed using branes and all that. Is there a reason why we cannot do that for n equals 2? Because it seems like in supergravity, it's just a matter of consistent truncation, but in the string theory side.
It's not that in string theory, it cannot be done. In string theory, certainly there are lots of string compactifications which have n equal to 2. You can take type 2 on Calabi-Yau, for example. Okay, that will give n equal to 2 supersymmetric string theories. Is that the counting is difficult? I don't think I can say why it has not been done. It's certainly more difficult.
Okay.
And nobody has been able to produce a counting formula for any kind of black hole, any kind of state here, which grows into a black hole. See, there are of course fundamental string states which you can count easily in these theories. But to get something which is a black hole, you have to put together the electric and magnetic charges appropriately, and then count their states, and that simply has not been done.
Okay. So,
right?
so an equivalent of what we, the partition the partition functions that you calculated, or the generating functions that you calculated, something similar to those has not been done. Is that what you're saying?
That's right. Yeah. So certainly construction of string theory has been done. There are many examples of n equal to 2 supersymmetric string theories.
Okay. Thank you.
Okay, I think maybe we should finish there. Let's thank Ashok again. Maybe people can unmute and applause because it's the last lecture.
Thank you.
Thanks for that very nice series of lectures. And if you want to continue the discussion, then I suggest gather. I mean, you can hang out here too.
And tomorrow we again meet at the usual time, right?
Yeah, at the usual time, and we'll talk about the format. We'll let you know what the format is in the afternoon today.
Okay. Okay. Thank you.
Yeah, but